This is Dr. Shankaraiah from Department of Physics. In this presentation, I am going to discuss question bank on Module 4, Magnetic and Superconducting Materials. So, this is Part B, which is on long answer questions. So, the first question is, explain the terms magnetic dipole moment, magnetic field intensity, and magnetic induction. So, what is a magnetic dipole? Magnetic dipole is a system in which two equal and opposite magnetic poles separated by a distance. This is called as magnetic pole. So, you have south pole, you have north pole, and these two poles are separated by some distance d, and that is what we are going to call it as a magnetic dipole. And this magnetic dipole produces magnetic moment, dipole moment, depending on the alignment with respect to the applied magnetic field. So, magnetic dipole moment is a product of pole strength and magnetic length. So, magnetic moment is equal to current into area of the circulating orbit. Okay. So, current is I and area of the, suppose if you are taking a circulating orbit in the form of circle, then the area of the circle is pi r square. So, the magnetic moment produced by a circulating orbit in the form of circle is I into pi r square. Okay. So, magnetic field in which a material is kept is called magnetizing field. The strength of the magnetic field is denoted by H, and the units of H are amperes turns per meter. So, magnetic field is produced by permanent magnets such as horseshoe magnet. Temporarily, you can produce by electromagnet or superconductor magnets. Magnetic induction. Magnetic field is schematically represented by magnetic induction, lines of magnetic induction, and it is described either by magnetic field strength H or magnetic induction or magnetic flux density. So, magnetic induction B is nothing but the magnetic lines, flux lines of induction. The lines of induction are collectively called as flux. Okay. So, magnetic induction is defined as number of field lines passing through a unit area of cross section is called magnetic flux density. So, B is equal to magnetic flux by unit area. So, magnetic flux per unit area is called as magnetic field induction, and units for magnetic field induction is Gauss or Tesla. And here 1 Tesla is 10 power 4 Gauss. Okay. So, basically we have described all these terms: magnetic dipole, dipole moment, magnetic field intensity, and magnetic induction. Second question is, discuss in detail about the magnetic permeability, relative permeability, intensity of magnetization, and magnetic susceptibility. Okay. So, first, permeability, magnetic permeability is when a material, magnetic material is placed in a magnetic field, the magnetic field lines are redistributed and tend to pass more or less through the material. So, basically, permeability is defined as it is a measure of the degree of which the field lines penetrate through the material. What is the degree of which field lines can penetrate through the material? So, that is defined as permeability, magnetic permeability of a material, and mu is equal to B by H. Okay, mu is magnetic permeability, mu is B by H, where B is magnetic induction and H is magnetic field, applied magnetic field. So, we are applying some magnetic field. So, how many magnetic flux lines are able to pass through the material? So, that will tell us about the magnetic permeability. Next one, relative permeability. So, the relative permeability is defined as a ratio of absolute permeability of the material and the permeability of free space. Okay. So, mu is equal to mu into mu divided by mu naught, or mu is equal to mu naught into mu r. Okay. So, from this equation only we got this mu is equal to mu naught into mu r. Okay. So, mu r is relative permeability, which is 1 for free space or air. So, the relation between this mu r and susceptibility is this. Okay. So, because mu is equal to mu naught into 1 plus chi, this we will get when discussing about the equation relation between B is equal to between B and H and M. So, using this equation, so if you substitute M is equal to chi into H, so mu naught into H plus chi into H, because M is equal to chi H, so you will get mu naught into H H you can take out common, mu naught H into 1 plus chi. Okay, so that is B, mu naught H into 1 plus chi. Okay, so yeah. So comparing this equation and this equation, we can, so from this, if I write this as B is equal to mu into H, for example, so where mu is equal to mu naught into 1 plus chi. So comparing this equation and this equation, we will find out that mu r is equal to 1 plus chi, or mu is equal to mu naught into 1 plus chi. So from this equation, we will get the relation between mu r and chi. So 1 plus. So this is very important equation which we have used in solving the numerical problems. That is relative permeability is equal to 1 plus chi, which is susceptibility. Okay. So this is relative permeability, and then the relation between relative permeability and susceptibility. Then magnetization. The magnetic moment per unit volume developed inside a solid is called magnetization. It is denoted by M, and amperes per meter is the unit. Since magnetization is induced by the applied magnetic field, we write as M proportional to H. We are removing the proportional constant by keeping a constant chi. So M is equal to chi H. Okay. So susceptibility is defined as the measure of the ease with which material can get magnetized. Okay. Susceptibility is a measure of the ease with which material can get magnetized. If the material has high susceptibility, it will easily get magnetized. If the material has low susceptibility, it will slowly get magnetized. So materials having high susceptibility are easily magnetized. So chi M is equal to chi H, or chi is defined as M by H. So I apply magnetic field, how much magnetization is produced or developed inside a material is called as susceptibility. Okay, so basically we have defined magnetic permeability, relative permeability, magnetization, and magnetic susceptibility. Obtain the relation between magnetic susceptibility, magnetization, and magnetic field intensity. Okay, so we know what is magnetization. Magnetization is magnetic moment per unit volume that is developed inside a solid. Okay, and units are amperes per meter. And because whenever we apply magnetic field, only then the material is getting magnetized. So we write M proportional to H, M is equal to chi H, right? So we know what is so M is equal that removing this proportional constant, we get chi H, right? So M is equal to chi H. So this is the relation between M, chi, and H. M magnetization, chi susceptibility, and H is the magnetic field intensity. Okay, so from this equation we can define what is chi susceptibility. It is a measure of the ease with which material can get magnetized. So I apply magnetic field and how much magnetization is produced inside the material. So that is the chi. Describe the origin of magnetic moment and find the magnetic dipole moments due to the orbital and electron motions of electron and spin motions of electron. Okay, so we need to discuss about the origin of magnetic moment. Okay, so the magnetic properties of solids arise due to electrons undergoing different motions. Magnetic properties of solids are coming from where? Electrons undergoing different motions in atoms, which gives rise to magnetic dipole moments. These magnetic dipole moments are responsible for the magnetic properties of materials. In general, the magnetic dipole moment of the atom arises from three sources. First one is orbital motion, second one is electron spin and nuclear spin. Okay, so what is orbital motion of electron? How it gives rise to the dipole moment? The atom of any material consists of a central nucleus, and the electron move around the nucleus in specific orbits. Each electron orbit is equivalent to a tiny current loop. So I have an orbit, this is the nucleus, and electron is revolving a nucleus in this circular orbit. This is a closed loop, and electron is running around in this closed loop. So that means it is a tiny current loop, okay, and behaves as an elementary magnetic moment. Whenever the charge electron is moving in a closed loop, it produces magnetic moment, and hence magnetic moment is produced. The total orbital magnetic moment of an atom is the sum of the orbital magnetic moments of all the independent or individual electrons. Now, how do we get the magnetic moment from the electron spin? Each electron is spinning about an axis through itself, and the spin also gives rise to a magnetic dipole moment. Apart from the electron motion, you can also have magnetic moment from nuclear spin. In addition to the electron contribution, nuclear spin contributes magnetic moment of the atoms. The magnetic moment of the nucleus is about 1 by 2000 of the magnetic moment of electrons. So therefore, in general, we neglect this magnetic moment coming from the nuclear spin. So the total magnetic moment of an atom is the sum of orbital and spin magnetic moments of electrons. Okay. So we can derive the equation for magnetic moment in orbital motion. Okay. So yeah, so we know that electron is revolving in circular orbits around nucleus, and we know that current is produced because of this. So the current is charge per time, and that is E by T. So I have defined time period in terms of angular frequency, which is 2 pi by omega. So I have substituted this T in this equation. So E by 2 pi by omega. So E omega by 2 pi, and I have defined magnetic moment mu as current into area, right? So current I have got it as E omega by 2 pi, and area is pi r square. This circular orbit pi cancel out. I get this equation E omega r square by 2. Okay, so I know the angular momentum of a charged particle L is r cross p. P is momentum, so I write it as mv, and then I write angular velocity as r into omega. So when I substitute r omega, so I get m omega r square. So now I know what is L, so I can substitute in this equation, which I have for mu, which is E omega r square by 2. So I know what is L. L is m omega r square. Okay, so E omega r square by 2. So I want to write this magnetic moment in terms of angular momentum. So okay, so then I can, so if I substitute this, L as m omega r square. In this equation I do not have m, so I'm going to multiply and divide by m. Okay, so multiply and divide by m, so I get m omega r square. So that will be basically E m omega r square. So EL by 2m. So that is why I get here EL by 2m, plus or minus, you can, depending on the clockwise and anti-clockwise direction of the electron that is spinning around the nucleus in circular orbit. But as per Bohr's atomic model, L is quantized, the angular momentum is quantized, which is LH by 2 pi is here, it is orbital quantum number is L. So I am going to substitute L as LH by 2 pi, so then I will get E into LH by 2m into 2 pi, so that is EH by 4 pi m into L. Okay. So EH by 4 pi m is defined as Bohr magneton, which is the unit of magnetic moment. Okay, it is clear from the equation that electron can take only certain specified values of magnetic moment depending on the value of orbital quantum. So this is the magnetic moment generated by the electron in orbital motion, which is EH by 4 pi m. So that is mu b into L, where mu b is Bohr magneton. Okay, so mu L, magnetic moment because of the orbital motion of electron, is plus or minus mu b into L. Similarly, magnetic moment produced due to the spin of electron, spin is quantized and it is plus or minus half. So we can write the magnetic moment because of the spin of the electron as plus or minus mu b. Okay. Similarly, yeah. So this is the electron spinning around itself, giving rise to magnetic moment, and electron spinning around the nucleus in circular arc. So because of the electron motion, we have two different types of magnetic moments. Orbital motion giving rise to magnetic moment, and spin of the electron is also giving rise to magnetic. Finally, the magnetic moment nuclear spin is very small, which is EH by 4 pi mp, and this is called as nuclear magneton. Okay, EH by 4 pi m, where m is mass of electron, so that is Bohr magneton, and it is EH by 4 pi mp, where mp is mass of proton. This is called as nuclear magneton. Nuclear magneton is very small compared to the Bohr magneton. What is a Bohr magneton and how is it related to the magnetic moment of electron? Bohr magneton is a small elementary electron magnetic moment. It is elementary in the sense that no electron can have a magnetic moment below it. It is natural unit for measurement of atomic magnetic moments. Okay, it is denoted by mu v is equal to EH by 4 pi m, and the value of Bohr magneton is this. Okay, so when we so how is it related to the magnetic moment? So then we can write about this orbital magnetic moment coming from the orbital motion, right? Magnetic moment in from orbital motion of electron. Orbital motion of electrons. Okay, so the magnetic moment coming from the orbital motion of electron. So that is mu L, which is equal to plus or minus mu B into L. Similarly, electron spin, magnetic moment coming from the electron spin, magnetic moment from electron spin. So electron spin, that is mu S is equal to plus or minus mu B. Similarly, magnetic moment, third one, magnetic moment is coming from nuclear spin. Okay, so that is mu N, which is equal to EH by 4 pi mmp. So that is nuclear magneton. Okay, so this is called nuclear magneton. So this is how Bohr magneton is related to the magnetic moment of electron and nucleus, right? So electron, orbital motion of electron, and you have Bohr magneton moment, magnetic moment, and spin of electron also gives rise to the magnetic moment. Discuss between diamagnetic, paramagnetic, and ferromagnetic materials. Explain their behavior with the help of examples. Okay. Diamagnetic materials, paramagnetic materials, and ferromagnetic materials. So diamagnetic materials repel the applied magnetic field. So if you apply magnetic field, diamagnetic materials repel the applied magnetic field. So that is the property. Paramagnetic materials are very attractive, weak attractive force to the applied magnetic field, whereas ferromagnetic materials have very strong attractive force to the applied magnetic fields. Next, the magnetic moment in diamagnetic material is coming from the orbital motion of electron, whereas the magnetic moment in paramagnetic material is coming from the spin of electrons. In ferromagnetic materials also due to the spin of electrons. These diamagnetic materials have no spin, whereas paramagnetic materials spin is random, and ferromagnetic materials all the spins are parallel. Diamagnetic materials are lack of magnetic dipoles. There are no permanent dipoles present in diamagnetic materials, whereas paramagnetic materials have permanent dipoles. Ferromagnetic materials also have permanent dipoles. Diamagnetic materials do not possess permanent dipole moment, and it is zero, hence spontaneous magnetization is also zero. Paramagnetic materials have permanent dipole moments, but their spontaneous magnetization is zero in the absence of external field, because all the spins are oriented randomly. Ferromagnetic materials have permanent dipole moment, and in the absence of field also they have spontaneous magnetization, because all the spins are oriented in single direction. The relative permeability is less than 1, actually negative for diamagnetic materials, less than 1 in diamagnetic materials and greater than 1 in paramagnetic materials, and very large for ferromagnetic materials. Susceptibility is small and negative for diamagnetic materials, whereas susceptibility is small and positive for para, small and large and positive for ferromagnetic materials. Okay, so the susceptibility does not depend on temperature in diamagnetic materials, and this is the dependence of chi, susceptibility on temperature in para and ferromagnetic materials. Okay, diamagnetic materials do not exhibit any hysteresis. Paramagnetic materials also do not exhibit any hysteresis, whereas ferromagnetic materials exhibit hysteresis. Examples of diamagnetic materials: copper, iron, zinc. Whereas para, aluminium, plutonium, and platinum and manganese. For ferromagnetic materials, iron, nickel, cobalt. Okay, so these are some differences and examples of dia, para, and ferromagnetic materials. Next question: illustrate the phenomenon of magnetization. Show that B is equal to mu naught into H plus M. Okay, so magnetization is nothing but the sum of all the magnetic moments of electrons in a material, and this magnetization is directly proportional to H, because whenever we apply field, the magnetic material getting magnetized, right? So this magnetization produced in a material coming from two parameters, right? So two types of induction arises when you keep the material in the magnetic field. One is due to the magnetizing field H, and the other as a consequence of magnetization in the material itself. So when the material is getting magnetized, it also produces the magnetic induction. Okay, so that is why magnetic induction B is equal to mu naught into H plus M. Okay. So you can we know that magnetization is directly proportional to H, or M is equal to chi into H. So when we substitute this equation in this M is equal to chi H, we are going to end up with this equation. Okay, where mu is equal to mu naught into 1 plus chi, and this is mu is called as permeability of medium, and mu naught is called as permeability of free space, which is 4 pi into 10 power minus 7. In the case of free space, M is equal to 0 and B is equal to mu naught into H. So we have discussed what is magnetization, and how do we get this equation B is equal to mu naught into H. So we need to define what is magnetization, how do we get how a material get magnetized, and then this magnetic induction is coming from two parameters, applied magnetic field and magnetization of the material itself. And then we can end up discuss about few things about B and H plus M. Draw the BH curve for a ferromagnetic material and identify the retentivity and coercive field on the curve. Okay, so this is the BH curve here. So if an initially unmagnetized specimen of a ferromagnetic material, so we take a ferromagnetic material, for example iron, when you do not apply any field, the magnetization is 0, and then if you subject this material to the increasing decreasing magnetic field, the magnetic field induction varies as a function of H in a closed loop. That loop is called as BH loop. So along x-axis you have H, and along y-axis you have B. Okay. So in the beginning, when we without applying magnetic field B is 0, as I apply magnetic field in this direction, the magnetic field induction increases slowly here. As I decrease the magnetic field, the magnetic induction also decreases, but when the field is 0, the magnetic induction is not 0, it is finite. Okay, so this magnetic field induction is called as residual magnetism, and this is the magnetization that is stored in the material even in the absence of magnetic field, which is called as residual magnetism. And the ability of the material to restore or store this magnetization in the absence of field is called as retentivity. Okay, now I have reversed the direction of applied magnetic field and I start increasing the magnetic field in this direction. Then the magnetic induction becomes 0 at some field. Okay, and the amount of field that is required to destroy the residual magnetism is called as coercive field. Okay, this is called the ability of the material to store magnetization is called retentivity or remanence, and the amount of field required to destroy the residual magnetism is called as coercive force. As I increase further and further, the magnetic induction increases and reaches a saturation because of the electrons that are getting oriented in the direction of magnetic field. You get a saturation in both directions. So here all the spins may be orienting in upward directions, and here all the spins might be orienting in a downward direction. So then even if you increase further and further, there is no other spin to get oriented. All the spins are oriented now. That is why it is reached saturation. Now as I remove the field, the magnetic induction decreases, but to a finite value, even though field is reduced to 0. Okay. So then as I change the direction of a field, increase further, and I find that this magnetic induction goes to 0, residual magnetism goes to 0. Again you have the coercive field here, and then as I increase further, this will close in a loop. So this closed loop is called as BH curve or hysteresis loop. And here you have retentivity or called remanence, and you also have coercive field or coercive force. Okay, so this is what we need to discuss about the BH curve. So there are 2 points where you can use. So this point C and this point F. In these 2 points you can use that piece of iron as a permanent magnet because there is residual magnetism present in the material. Explain soft and hard magnetic materials. Based on the area of the hysteresis loop, magnetic materials are broadly categorized into 2 categories: soft magnetic materials and hard magnetic materials, based on the area of the hysteresis loop. Okay, so in hysteresis loop, when we calculate this, when we look at this hysteresis loop, there is area. This area, the area under this curve can be used to calculate the energy loss in a ferromagnetic material. Okay. So based on this area of this ferromagnetic material, you can classify magnetic materials into 2 categories: soft and hard magnetic materials. So if The area within a hysteresis loop represents a magnetic energy loss per unit volume of the material per magnetization-demagnetization cycle. The energy loss is manifested as heat that is generated within the specimen and raises the temperature of the material. So magnetic materials which are easily magnetized and demagnetized are known as soft magnetic materials. They are characterized by thin hysteresis loop. So soft magnetic materials have very thin hysteresis loop. Okay. In applications where the material is subjected to AC fields, materials having narrow and small area hysteresis loop are to be used. Hard magnetic materials are those which have a high resistance to demagnetization and large area hysteresis loop. Okay. So large area hysteresis loop, these magnetic materials are called as hard magnetic materials. High remanence, high permeability, high coercive field and high hysteresis, large hysteresis loop characterize the hard magnetic materials. In some applications, the magnetization of the material is to be retained on a permanent basis. Materials with large area hysteresis loop are more suitable for this purpose. Explain the hysteresis loop in a ferromagnetic material in reference to the domain theory. Okay. So we are going to discuss, just now we have discussed about this hysteresis loop. Here they are saying that related to the domain theory. Okay. So now when we say that domain theory, domain is nothing but you have a magnetic material. So in a magnetic material, for example, in the absence of field, all the spins are randomly oriented. That is why the magnetization is zero. All the spins of electrons are randomly oriented in a magnetic material. In the absence of field, H is equal to 0. As you increase the field, what happens? These spins are going to tend to orient. So here some of the spins are oriented in one direction. Here some of the spins are oriented in some other direction. Here another spins are oriented in the other. Okay. So there are regions where you have spins oriented in one single direction. Those regions are called domains. Okay. So this picture belongs here, no magnetization. So as you increase further and further, this picture belongs here. Here in this, at this point of saturation, all the spins present in the magnetic materials are oriented. For example, if I am applying the field in this direction, all the spins are oriented in the direction of magnetic field. That is the reason why I am getting saturation in the magnetization. Okay. So when you apply when you started increasing the magnetic field, you see that these spins are slowly started orienting locally, and those regions where you have local orientation or arrangement of spins in single direction those are called as domains. And as you increase the field further and further, all the spins tend to orient in a single direction. This is how you get saturation in the magnetization. So yeah, using this domain theory, you can explain that why do you get saturation in the magnetization, and why do you, even though the field is decreased to 0, or the sum of the spins are not become random. Okay, so that is why you have some residual magnetism, and when you apply the field in the reverse direction, all those spins will become random, and that is why you get zero magnetic induction. So explaining the magnetic domain theory, we can explain this hysteresis loop, which is used to calculate the energy loss of a ferromagnetic material. So to summarize, in this presentation I have discussed the long answer questions of module 4. Yeah, thank you.
Like, share and subscribe. Hit the bell icon for more updates.